Today we're going to be talking about Newton's law of universal gravity. So this is going to be talking about how gravity affects everything in the universe, and this one law pertains to everything that has mass. If you remember a few school days ago, we had the acceleration of gravity in all these different places in the solar system of the same little big dude in different places. Like if he's out in the middle of nowhere, 0 acceleration. If he's near the moon, 1.6 meters per second squared. If he's near Earth, 9.8 meters per second squared. So what we're going to talk about today has something to do with these numbers in a way. It's what affected these numbers, right? What was the thing that affected them? So today, let's talk about the force of gravity between two objects. Let's compare the force of gravity of the dude when he's standing on Jupiter, force of gravity pulling down at point C, when he's standing on Jupiter, versus the same dude way out here far away from Jupiter at point B. Which of these two places, both these dudes are pulled toward Jupiter, okay, because Jupiter has gravity and it's going to affect everything around it. But which of these two guys, the guy at B or the guy at C, which of these two guys would have the greatest force of gravity pulling him down? Or would they have the same force of gravity? What do you think? And why? So the guy on Jupiter would have the strongest force of gravity because he's standing right there on the planet. This guy's really far away. So since he's so far away, he's not affected by the gravity as much. That makes sense. Now, how about this though? What about if I had two different objects at the same distance away from Jupiter? What if I had this moon and I had the guy, and they're both way out here the same distance away from Jupiter? Which of these two would have the biggest force of gravity, or they have the same force of gravity pulling them towards the same planet, Jupiter? Obviously, the moon, this big, huge moon, would have more force of gravity, more weight than this guy, because the moon has more mass, so it's going to be pulled even more strongly towards the planet. So what we're talking about, we're going to try to turn this into an equation, all right? So things that will obviously affect the force of attraction between any two objects is the mass of the first object and the mass of the second object and the distance between them. These are the three things that are going to affect the pull of gravity between any two objects. This could be a dude out here and Jupiter, or it could be the moon and Jupiter, or it could be the dude and the moon, or it could be the moon and the Earth, or any two objects. Any two objects, an apple and the Jupiter, okay? And their distance between them and their masses. Mass of object 1, mass of object 2, and the distance between them. These are the same. These are any two objects. This one here is, I just made them two spheres, two spherical objects. Mass 1, mass 2, and the distance between them. So what we're going to try to do is figure out where each of these three things goes on this fraction for the force of gravity pulling them together. So remember, anything that we put on top of this fraction will be directly proportional to the force of gravity, because when anything on top gets bigger, it makes the whole fraction bigger, and since they're equal, it will make the force of gravity bigger. So things on top of the fraction are going to be directly proportional to gravity. Anything on the bottom of the fraction is inversely proportional to force of gravity over the weight, because when you make this bigger on the bottom, you're dividing by a big number, which makes the fraction smaller, which makes force of gravity smaller. So anything on the bottom is going to be inversely proportional. So let's figure this out. The mass of one object, mass of the second object, and the distance between them, where do they go in this fraction? Which ones go on top, which ones go on the bottom, or do they all go on the top, or they all go on the bottom? What do you think? Let's start with mass of the second object, like the mass of the planet, Jupiter, for example, or Earth, whatever the mass of the object is. Do you think mass 2, is this going to go on top or the bottom? All right, here's how you should think about it. More mass, when you have more mass, a bigger planet, is that going to be more force of gravity or less force of gravity? In other words, is mass going to be directly proportional or inversely proportional to the force of gravity? Where does mass 2 go, on top or bottom? Right, mass 2 goes on top. because more mass means it's going to be pulled more strongly, so more force of gravity. So it goes on top because this mass is directly proportional to form. When this goes up, force of gravity goes up. Now, what about the mass of the outer object, the mass of the moon out here, or the guy out here from in space? How does this affect the force of gravity of attraction between the two objects? Is the mass of the guy, the mass of the other object, is it going to be on top or the bottom? Right, mass 1 also goes on top because, again, more mass of the second object, the more mass the guy has, the more mass the moon has. Mass means more force of gravity, so it goes on top. Both masses are directly proportional to the weight or the force of gravity. All right, we have distance left. Now, the distance between them. How does distance affect the force of gravity between the two objects? More distance means more force of gravity, or more distance means less force of gravity? What do you think? Does distance go on top or bottom? Is distance directly or inversely proportional to the force of gravity between two objects? Distance goes on the bottom because the farther apart these are, the farther apart they are, the lower the force of gravity. More distance means less force of attraction. So there you go. You figured out Newton's second law is actually just like that, except something you couldn't have known. But what we figured out is that it's actually distance squared. Distance squared. Mass is on the top and distance squared on the bottom. We'll come back to that later. Let's talk about objects being pulled to the earth. Well, let's say I had an apple, okay, and I had it way above the earth, and I dropped it, let go of it. It would just fall, with no horizontal velocity. It would just fall straight down towards the earth. It'll fall at 9.8 meters per second squared and fall straight down towards the earth, just like that. Now, something interesting happens. Let's do a thought experiment. What if I took the apple, instead of dropping the apple, what if I instead threw the apple sideways like that? If I gave the apple some sideways velocity, do you think it's going to fall straight down? No, it'll start moving to the right. But gravity's still going to pull it down, right? So if I threw it sideways, gravity's still going to pull it down. It just, what will happen is the apple will move more to the right, and as gravity pulls it down, it'll land farther over here. Okay, so this is like throwing really fast, but gravity's still going to pull it down, and it'll just land over here somewhere. What if I threw it even faster? Okay, if I throw it fast enough, imagine what will happen. It will go so far that even though it's falling towards the earth, it won't actually ever hit the earth like that. This is called an orbit. This is how we get something in orbit, right? If it goes fast enough sideways, even though it's falling downwards, it never actually reaches the earth. We have to have just the right velocity, and it'll go in an orbit. What do you think will happen if I throw it even harder than this? Like that. It will leave orbit of Earth. All right, so what I need you guys to do today, your assignment today is actually pretty easy. I need you to get this note strip, Unit 6.2. It has that picture that we just showed you, Unit 6.2, and glue it in to your notebook on your next blank page. I bet this is on page 43 probably, but glue it into your next blank page. When you're done with these notes, it'll look something like this. So go ahead and glue in these notes, and then we will finish up some of these notes today. Here's our picture, the apple falling, a little bit of sideways velocity, and then even more velocity, it goes in orbit. So orbiting objects are in free fall. Go ahead and write that down. Orbiting objects are in free fall. They're falling at 9.8 meters per second squared towards the center of the Earth. It's just that they're moving sideways so fast they never actually hit the Earth. Think about this. The moon itself is an orbiting object. It is falling. The moon is falling straight towards the center of the Earth. The acceleration is towards the center of the Earth. It's just that the moon is moving so fast sideways, it never actually hits the Earth. Next time you look up at the moon, think about that. Okay? Look up at the moon and realize that thing, nothing's holding it in the air. Nothing is holding the moon up in the air. It is falling towards Earth, just like everything else is falling towards Earth. All those satellites up there, the International Space Station, they're all falling towards Earth. It's just they're all moving sideways so quickly they never actually reach the Earth. They keep moving sideways and missing the Earth. So that's actually kind of the amazing thing that Sir Isaac Newton discovered. The centripetal force that holds the planets in orbit around the sun is the same force that pulls an apple towards the ground. This is why it's called the law of universal gravity, because it applies to everything. Apples being pulled to the ground, planets being pulled towards the sun, the moon being pulled towards the earth. All right, we're going to finish up with a picture that goes with the force of gravity. The gravitational force is the mutual force of attraction between particles of matter. So our picture is going to look something like this. So I'll get a close-up picture of that. Go ahead and draw. This will be two objects, for example, the moon and the earth, and the force of gravity between them. Make these arrows the same lengths of each other because it's the exact same amount of force. The moon's being pulled towards the earth and the earth is being pulled towards the moon. The exact same force. This is Newton's third law. For every action, there's an equal and opposite reaction. And then mass 1 is the mass of the moon, and mass 2 is the mass of the earth. Draw that in there, and then we also want to add the distance between them. Okay, the distance, and it's between the centers, the center of the moon and the center of the earth. This is the distance between them. And then finally, we get back to our equation. This is the equation that Newton discovered. And this is something similar to what you guys came up with. Mass 1 is mass of one object, mass 2 is mass of the other objects in kilograms, and this is the distance between the centers of the objects in meters, but it's actually distance squared. And then we do have to add one more thing that you couldn't have realized is big G. We need this big G in there. This is the gravitational constant of the universe, the gravitational constant of the universe. We have to add this because this turns, let's see, this, because this is going to be kilograms over meters squared. So it's going to be kilograms squared over meters squared. And that has to somehow become Newton's force. So this G turns kilograms squared per meter squared. It turns it into Newton. So the equation works out. So there's our equation, a universal gravity. We're going to be using this for the next few days. And this will be a very important equation on your quiz that when you guys get back, your common informal assessment when you get back. And just to kind of put this in perspective, again, this works for any two objects like this guy out in the middle of space being pulled towards Jupiter and the distance between the guy and Jupiter and the mass of the guy and the mass of Jupiter. You can plug these into this equation if you do big G and figure out the force of attraction between them. It works for any two objects in the universe, any two objects that has mass.